Okay, in this video, we're going to talk about relativity basics. And what we mean by that is what happens when subatomic particles travel with very high speeds close to the speed of light. So I'm going to improvise a lot in this video because the things you need to know are kind of simple and basic, but then to understand them, you have to go into a little bit of depth with regards to math. So I'm going to tell you all you need to know in upfront, and then we will try to prove what we write right now. So let's start by what you actually need to know is that particles in motion gain mass and appear to be heavier. Okay. So what kind of particles are we talking about? We are talking about subatomic particles, electrons, protons, maybe some light nuclei, oxygen-16, stuff like that. We're not talking about vehicles or really massive objects like that, okay? Though the same principle applies to those objects as well, but we are not dealing with that right now. So what we mean by gaining mass is that if we have a proton traveling with a speed 98% the speed of light, for example, it will become heavier, it will gain mass, okay? And we will see how this happens in a moment. And the second thing you need to know is that time moves slower for moving objects. And again, we are talking about things that travel with speeds close to the speed of light. So if, for example, we had a spaceship that was traveling with 50% the speed of light from here to, I don't know, another star system, and back with the same speed, we would notice that maybe here on Earth, I don't know, 100 years passed, whereas for the astronauts in that spaceship, 10 years passed, okay? Does this happen for low speeds? It does, but we're talking about milliseconds, less than milliseconds, like 10 to the nanoseconds, stuff like that, okay? We will see why this happens as well. And the third thing you need to know is that c is the ultimate speed. It's the ultimate speed anything can travel with. So photons, by definition, move with the speed of light, okay? And the same is true for massless particles. The only massless particles that we are aware of currently are neutrinos and photons. And then you have also the graviton, which is hypothesized, and gluons as well, but we don't care about that. Let's keep it simple. So photons travel with the speed of light. And then if a particle has mass, it can actually never reach the speed of light, because to do that, we will need to provide an infinite amount of energy to the particle, which is impossible, okay? So even for electrons, which are light enough, when we are talking about facilities like SLAG, they can only accelerate electrons to a speed of about 99.9999% the speed of light, but never 100%, okay? So that's it. This is all you need to know about relativity and particles. So let's stop the video. No. Actually, we will keep moving, and now we will dive into some relativistic thoughts and math, which are kind of optional, but it will help you, I hope, understand what's going on. So let's also mention, before mentioning anything about relativity, that if the kinetic energy is 1/2 mv squared, and if v is not bound by c, and what I mean by that is that, remember, we just said that v can only be as high as the speed of light or less for any particle, okay? But let's assume that this was not the case, okay? So if the kinetic energy is that, and if v can exceed the speed of light, then we see that kinetic energy can become infinite, okay, which is impossible, okay, because energy must be conserved, so the total energy, so for everything in the universe, mass, energy, which are interrelated, must be conserved. And actually, let me drag this down here and right here that mass energy are interrelated. Okay, let's bring this there. There you go. Okay, in the video where we talked about particle accelerators, and I'm going to provide a link to the video, okay, we did show two things: that V is lesser than or equal to C for all particles, and that the kinetic energy for a particle moving with relativistic speeds, which are approximately 0.05 the speed of light, or 5% of the speed of light or more, so that's about the limit of what we consider relativistic, the kinetic energy is gamma minus 1 mu c squared. Okay, I'm going to put this in a red box because this is optional. This is not something that you need to know for A-level physics because this is a little bit advanced, but it does help in understanding what's going on. So before saying anything more about the kinetic energy, let's go talk about what gamma is. Gamma is given by 1 over the square root of 1 minus v over c, both squared. Okay, so since v is lesser than or equal to c, gamma is always more than or equal to 1. So if the speed of a particle is 0, then we see that gamma is 1. If the speed of a particle is, say, 0.5 c, or 50% the speed of light, then gamma is 1 over the square root of 1 minus 0.5 squared, since the c is cancelled. So gamma ends up being 1.15, okay? And this is what we mean by mass increasing. Remember when we said that particles in motion gain mass and appear to be heavier? As we will see in a while, this is because of this gamma factor. Okay, this happens because of this gamma factor. So let's go mention one more thing before moving on. So what happened there? Okay. So let's mention one more thing before moving on. So since kinetic energy is gamma minus 1 mu c squared, and by the way, mu is the mass of a particle when v is 0. That's why it's called the rest mass. It's the mass of a particle when it's not moving, okay? So since that's the kinetic energy, and because gamma is given by 1 over the square root of 1 minus v over c squared, we see that if v is much smaller than c, okay, sorry, let's put it this way. If v is much smaller than c, okay, then 1 over the square root of 1 minus v over c squared is approximately equal to 1 plus v over 2c squared. And I'm not going to prove this, but let's do one simple calculation. So say if v is v over c is 0.04, okay, then 1 over the square root of 1 minus 0.04 squared is 1.0008, and 1 plus 0.04 squared over 2 is also 1.0008. It's not a mathematical proof, but you can see how this works, okay? So this is called an approximation. So what we did here, this is an approximation of this function. Okay, so this is the function, and we expand it, and if v over c is much smaller than c, these two are equal. Okay, so we see that. So if v is much smaller than c, then kinetic energy is, remember, it's gamma minus 1 mu c squared. So this becomes 1 plus v squared over 2c squared minus 1 mu c squared. These ones cancel, and this also cancels. So we get 1/2 mu v squared. So we recover the kinetic energy we are familiar with in Newtonian mechanics, pretty much, in Newtonian physics. Okay, so it all makes sense, hopefully. Now, we talked about the kinetic energy so far. So let's go talk a little bit more about other things. So for particles at rest in relativity, we have that the total energy is equal to mu c squared. Okay, so the total energy of a particle is mu c squared. So even particles at rest have energy, so you have to convert their mass into energy. Okay, so this is usually used for subatomic particles, not massive objects. Okay, even though it applies to to massive objects as well. So if you had a way to convert me into energy, an enormous amount of energy would be created, but that's not easy to do with massive objects. It only works with subatomic particles. Okay, so the total energy is mu c squared if v is 0, if a particle, so if v is 0, so particle at rest. So this is also called the rest mass, rest energy, sorry, not mass, so rest energy. Now, if particles, for particles in motion, the total energy is equal to gamma mu naught c squared. Okay, and since gamma is larger than or equal to 1, we see immediately that moving particles gain mass, which is what you actually need to know. So this goes beyond, as I mentioned. Okay, let's put this in the red box as well. And also, remember that earlier I told you that the kinetic energy, where is it? The kinetic energy is gamma minus 1 mu c squared. Let's go see why. Okay, so here we talked about the total energy, the way it's defined in relativity. Now, total energy, so sorry, let me use black. The total energy is equal to the kinetic energy plus the energy that a particle has due to its mass, the rest energy. Okay, so every particle carries this factor here. Okay, it's just that we just proved earlier how for really low speeds we recover this kinetic energy. Okay, but the total energy is equal to the kinetic energy plus mu c squared in relativity. Okay, so notice how, since the total energy is gamma mu c squared, and this is equal to the kinetic energy plus mu c squared, which is the energy a particle always has due to its mass, then the kinetic energy is mu c squared gamma minus 1. Okay, let's see this gamma factor in action. So let's do an example. So we have the example of a proton moving with velocity 0.999 c. Okay, the mass of the proton is at rest when it's not moving. M naught is 1.67 times 10 to the negative 27 kilograms, okay? Now, m nu c squared is, if we convert all of this mass of the proton into energy, how much energy will you get? We get 1.67 times 10 to the negative 27 times 3 times 10 to the 8 squared. Remember, always use parentheses when you do these kind of calculations to avoid errors, okay? And then the units are kilograms meter squared over second squared, and all of you will recognize that this is 1 joule, okay? So this gives me 1.5 times 10 to the negative 10 joules, and since 1 electron volt is 1.6 times 10 to the negative 19 joules, we find that m nu c squared is 939.4 MeVs for a proton. Is that a large energy? It is, right? Remember when we talked about particle accelerators? 1 electron volt is the energy of a particle that has a charge of plus E, so 1 electron or 1 proton, when accelerated through a potential energy, through an electric potential of 1 volt. So here it's like it's like accelerating this proton through a potential difference of 900 megavolts. That's a huge potential, okay? So a proton at rest carries a lot of energy, okay? Now we accelerate this proton to this velocity, okay? And I forgot to write that this is optional still, okay? This is not something anyone will make you calculate, but I just want to show you why we say that mass increases, okay? So even at rest, it has this energy. Now, let's calculate the gamma factor since it's moving with 99.9% the speed of light. So we have 1 over the square root of 1 minus 0.999 squared. If we calculate this, we find 22.36, okay? Gamma is a pure number, okay? Always remember that. So the total energy of this proton is gamma mu c squared. So 22.36 times 939.4 MeVs, which is 21.01 GeVs, okay? So it appears as if the mass increases from 939.4 MeVs, which is the rest energy or the rest mass of this proton, to 21 GeVs, okay? So it gains mass as it accelerates, okay? Let's go see an application. This is something that can actually be asked from you in an actual test. So let's talk about the discovery of the antiproton. We will talk about the antiproton in a moment, but for now, let's say that an antiproton is a proton with negative charge. Okay, so to discover this, they made 2 protons collide, okay, and we had the production of 3 protons plus 1 antiproton, okay? So does this make sense? Yes, because we have 2 charges before and then 2 charges after, because the positive and the negative charge kind of cancel here. So this is a possible reaction. But in terms of masses, we are dealing with 2 protons before that have energy of a rest mass of 239.4 MeVs, and after we have 4 protons, so 4 times 939.4 MeVs. So remember when I said that mass energy is conserved? In this reaction, it's not conserved. So the only way you can make this reaction possible is to provide energy. So in this reaction, we have a violation of mass energy conservation. So, but it works because particles in motion gain mass. Okay, so since mass and energy are equivalent due to E equals mc squared, we see that in this reaction, the total energy before and the total energy after are conserved via the production of a pair of a proton and an antiproton. Okay, I hope this makes sense. Guys, please ask questions in the comments when things don't make sense. And I also set up a Discord server that I visit every now and then. So if you go and ask me questions there, I'm gonna respond. So as far as particles gaining mass as they speed up, I think we covered everything you need to know. We covered more than everything you need to know. And the next thing I want to talk about is where this gamma factor comes from. Okay, and I'm also going to talk about how moving objects move slower. Okay, so let's go start a clean page. So again, this is also optional. The origin of gamma equal to 1 over the square root of 1 minus v over c squared. Okay, let me make some space. And also here we're going to prove that time moves slower for moving objects. Let's assume that we have a moving train. Okay, so this is the train. This is the cart of the train, say. The train is moving with velocity v, and there is a passenger in there. Okay, boy or girl, doesn't matter. So passenger, okay, and he has a stopwatch, okay, and a laser pulse and a mirror. So let's say that we have a mirror on the ceiling of the cart, and we have a laser beam. Okay, so this is the laser, and we shoot a laser beam up, and we detect it when it comes down. Okay, so we send a laser pulse to the ceiling, and it reflects on the ceiling and comes back. So from the point of view of the passenger, this laser pulse goes vertically up and comes vertically down, covering a distance of, let's call it y. Okay, so the passenger measures the time between shooting the pulse and detecting it when it comes back. Okay, so remember that v is delta x over delta t, right? So in this case, so t for the pulse to go back and forth is 2y, which is the distance the pulse covered over its speed. This is a laser speed, it's light, so speed is equal to c, the speed of light. Okay, so this is our first result. Now, at the same time that the passenger is measuring the time needed for the pulse to go up and down, there is a spectator. So let's draw this situation again. Train moves to the right with velocity v, and there is a spectator over here. So spectator, his or her velocity is 0, and they also measure the time needed for the pulse to go up and down. So they measure t prime, which is the time for the pulse to go up and down. But from their point of view, if this is the mirror, since the train travels to the right, they will see this. They will see the pulse traveling diagonally, okay? Let's call this distance L. And now recognize that this x is equal to v times t prime, okay? So from their point of view, t prime is 2L over C. So this is the time needed for the pulse to go up and down. But this time diagonally, and the reason why it's diagonally is because the train travels, okay? So it's not gonna, okay, this is exaggerated, but imagine that the train moves with a relativistic speed, then it will appear diagonal, okay? Now, remember that, actually, let me draw it over here. So let's draw the triangle. So this is the situation. We said that this is equal to V times T prime. This is L, and this was Y, right? Remember that? So notice this is a right triangle. So Y squared plus VT prime over 2 squared, because we are dealing with this side. So X over 2 is VT prime over 2, okay? So Y squared plus VT prime squared over 2 is L squared, but recall that Y is CT over 2, we showed that earlier, plus VT prime over 2 squared is equal to L, and L is nothing more than T prime C over 2 squared. So these two cancel, and we find that C squared T squared plus V squared T prime squared is C squared T prime squared. And if we bring everything to one side, we have T prime squared is C squared T squared over C squared. When we factor out 1 minus V squared over C squared, this C squared cancels. And immediately we see that we have T prime is T over the square root of 1 minus V squared over C squared, which is nothing more than gamma T. So this is where this gamma comes from. And I'm going to close this video by saying that moving things, actually for moving things, sorry. So for moving objects, time moves slower. And that's because of this gamma factor over there, okay? And this is where gamma comes from in relativity, and I'm going to stop here, and in the next videos we're going to talk about particles and such.